This is Polarized Light Microscopy in Archaeology, and this is Lecture 10, Other Materials in Thin Section. And so this is a result of looking what else is being done in the archaeological world by using polarized light microscopy. And so it's essentially just looking at what other people have done. This might actually be a good subject matter for a class presentation in the next term, finding something that interests you other than pottery. So, just something completely random. Apparently this is what beer looks like under polarized light. This is what wine looks like in polarized light. I just got these from somewhere or other because I thought they looked pretty. There's actually no archaeological relevance to this, but it does look quite attractive. However, shells are quite useful things to look at by looking at the section of them. You can do things like age them, see how old they are. You can see what environment they lived in. Each of these lines here are growth rings, annual growth rings, and so by counting these rings, shall we say, you can age it by looking at when they were deposited as calcium carbonate. You will often find there's a seasonal difference, so seasonality of when the thing died is relevant here. And so you'll be able to see that some seasons are better than others. Maybe a dry season or a cold season, there'll be less growth, and there'll be more growth in a more benign season. And you'll be able to see that, and also you'll be able to see which of the seasons that was in when possibly this shell was collected and its contents was consumed by humans. That's the archaeological relevance of that. So a number of things we're looking at aging and environment and seasonality by looking at these basically signs of the growth of the organism. So this is a bivalve. This is an otolith. This is a bone you get in the ears of fish. And this also has very distinct growth rings. And so just as with the shell, you can do a section through it, and you can even like etch it and count it as well, but some people actually put a thin section through it and count the rings, look at the seasonality, and look at the environment of that this fish has lived in. So otoliths. Teeth. So teeth are mostly made of calcium carbonate, growing in the enamel here and in the dentin here. So it has roots, and there's the painful bit here with the still alive. The enamel is made up of growth, prisms of calcium carbonate. That's what the lines going this way are made of. And they grow but have a pause called a line of Rexius, or a Rexius line. And these indicate chronological contemporaneity. Okay? So basically they're not like annual growth rings, but they grow a bit and they grow a bit and they grow a bit. And so you can then thereby say something about the seasonality and the growth of the organism that had these teeth. And you can also see perhaps if there was a problem in that growth with a bad season or exceptionally good season in the growth of the tooth. So here are those Rexius lines in a cross section of a tooth. Like that. And in the dentine there are also von Ebner lines in this case, indicating chronological contemporaneity. So the tooth growing in the jaw in a young individual before it erupts. So bone. Bone is also quite interesting. We get a lot of bones in the archaeological record, including human bone. This actually looks like a human bone and shows the kind of structure of bone. You'll have the compact bone here and the long bones, you see, and you'll have the spongy bone at each end. You have the periosteum and the endosteum. There you go, periosteum. Actually, that's not how you spell periosteum. Never mind. Compact and cortical bone, and the spongy or trabecular or cancellous bone. Let's just call it spongy. So how organisms grow their bones. Bones can be built up on the outside in these lamellar bone growths like this, but they're also replaced. They have these things called osteoblasts, which go through the bone, removing all of it, and then it's replaced by these concentric rings, which are called osteons. And so this is the structure of bone. So when you want to thin section bone, or a white material, it might be to identify that it's in fact bone. And you can see these osteons in the bone. And that's very different from, say, ivory, where it's all concentric, tooth-like construction of the material. So a thing about this was first written up by an anthropologist called Donald Ortner in 1975, that you can see effects of aging on the osteon remodeling. So he found that the degree of remodeling is consistent through time, and so what happens is the more osteons there are, the older the individual is. And they eventually found out that you can, in fact, work out precisely how old an individual is by this technique. This is 60 years and older, and this is like an infant. This is, I think it's the only way of providing an age to an older individual, when all the epiphyses have fused on the bones and all the everything is fused together properly, all the teeth have erupted. There's not a lot of evidence for the age of an individual past, like, say, 25 or so. And so what you do have is this. So this is an important technique for people who study human osteology to age the populations of skeletons they're looking at. So, yeah, something else you can do with thin sections. In fact, we have actually done this at the ROM. So here's some pictures of thin sections of bones. This is a toad, and so you can see there's none of those osteons going on. It's just lamellae, and so it probably doesn't live long enough to develop osteons. Here's a human, and here you can see the osteons. This big one here has actually got an osteon within the osteon. That happens sometimes. This one looks like it's starting to build up after having an osteoblast make the hole in the first place. So this remodeling is how bones will grow and stay strong. This is another bone with some osteons. Lots of lamellar bone on the outside, showing how this individual was continuing to grow. The outside of the bones possibly getting stronger or getting bigger, and that's the growth from that, whereas this is simple remodeling after it has achieved an appropriate size. This is a very different thing. Another thing you can look at is if there's something wrong with the individual, and the way this is deteriorating is apparently due to Paget's disease. And so that's another interesting thing you can find by looking at bone in thin section. And of course, there's all sorts of other materials other than pottery. Bricks, for instance, but also what keeps bricks together, mortar. And so here you can see the matrix here is lime, very similar to calcium carbonate. In fact, a lot of the calcium carbonate you may see has been turned to lime by the firing process. And in it there are all sorts of inclusions. So it is possible to actually thin section the mortar to see what was in it. You might be able to differentiate between different phases of construction of a building, looking at how the mortar was put together. Could be all sorts of fun things you can do with mortar. And there's micromorphology. You, of course, if you are archaeologists, I hope you are aware of stratigraphy, where there's this thing called microstratigraphy, which you may also have heard of. The only way you can see microstratigraphy is if you look down a microscope. So here are some microscopic pictures of depositions, archaeological deposits. This is a human coprolite from an Anglo-Saxon level in England with phytoliths. I've talked to you about phytoliths before. This is a dog coprolite. Seems to be a lot of coprolites. You can see partly digested bone in here. Yeah, you have to keep looking at that. This looks much nicer, doesn't it? This is from Chattel Hoyuk. And the deposit adjacent to a hearth. There was a lot of microstratigraphy done at Chattel Hoyuk. It was very important work. It includes fragments of charred oak wood. There you go. And mixed with trample from underlying plaster floors. What this is down here, actually. And also they thin section the wall plasters. And it was very interesting to see that the walls were repeatedly replastered and repainted. And you can see layer after layer of major plastering and then minor touch-ups of the plaster walls, which was a very interesting finding, I thought. So this is Katara Cave, a very important archaeological site. This has complex spongy microstructure composed of charcoal fragments and aggregates of organic matter. This looks like charcoal. Pale grey irregular aggregates are probably composed of poorly crystallized leucophosphite. Oh God. Well, you know what phosphate is, right? So phosphate, of course, you know the properties of phosphate, so you'd be able to recognize this in thin section. But phosphate is due to deposits by, well, probably humans. You get a lot of phosphates around cesspits, for instance. Anyway, so let's move on. This is Boxgrove. Very important archaeological site from the Middle Pleistocene. Acheulean bifaces all over the place. And you can see here the basically a sedimentary environment. There don't seem any floors in here of the deposition of the hand axes. Here's another Midden from England. With lots of sand grains in it, and bugs caused by the percolation of organic rich solutions derived from urine. So if you don't like that sort of thing, you might not want to get into micromorphology or microstratigraphy. Okay, this looks like another floor. Oh, animal waste. Okay, there's animal waste in this one. Okay, so they all have... Yes, the fuel is using cow dung. Okay, let's move along. Is there anything in here? Okay. These dusty clay coatings provide evidence of arid cultivation. So this is probably a field or something. And here, this is quite important, we'll get to this in a minute, is wood ash embedded in a floor of a cave. So, and they'd be able to identify the ash, the wood from that. And soil micromorphology, of course. Soil is very important. This is a light yellow limpid clay infilling from a Middle Pleistocene pyroclast layer. You know about pyroclasts, right? And this is opalized burnt grass. So phytoliths from a soil. So just a couple of soils there. Fibre identification is quite important. If you're looking at textiles, even quite extant textiles, you may not be able to identify the fibre unless you get a little bit of it and put it under polarized light. So fibre identification is actually quite a big thing for people who study textiles, and there is some major research being done on it. This is linen, Linum usistaticum, which you very important in Egypt, of course, and this is how you identify it. Another thing you might find on archaeological sites is remains of wood, and this makes some very attractive thin sections. And here you can see these are woods where they've taken a bit of a tree and put in there of particular species, box and viburnum and maple and I don't know what juglans is exactly. And you can see here it's just pore size, big pores, medium pores, small pores, teeny weeny pores. And you have interesting patterns as well. All of these are distinctive patterns to that type of wood. And you can quite often see distinctive patterns as wood. And you think, oh, that's like, for instance, you can probably easily tell the difference between oak and pine if you've ever looked at wood at all. But every type of wood will have a distinctive pattern, which you can clearly see in thin section. And here's some archaeological wood identification using thin sections. This is ash from a site in Ljubljana, Slovenia. And here's an oak from Ljubljana. You can see very different structures enabling identification. So that's just a taste of all the things you can see in thin section if you really try. And of course there are more than that. There's lots of things you can put in thin section. Just put anything in a thin section and see what happens. And you never know what you can see. Thank you.